today. So the classwork from today, there were two problems. These are both Faraday's law problems. The first problem says that you want to consider a loop of wire with some radius of A and resistance of R. And now reading this, I realize I could have worded this a little bit better. But what you're meant to think here is that here's some circular loop that has some radius of A, and it has a resistance of R. So that's the same thing as saying that I can put some resistor on here like this. And then there's also some magnetic field in this region where B vector is going to be equal to B0 times 1 minus t squared divided by tau squared. And this magnetic field is going to be pointing into the board. Okay. And what we want to find is we want to find the current and the direction of the current that's induced in this loop of wire. So the first thing that we can do is write down Faraday's law. So the integral over some closed loop of E dot dl is equal to the negative partial derivative with respect to time of the integral of B dot dA. Okay. So the next thing that we can do is we can choose what the direction of dA is, and by association the direction of dl. So as I said in class, I tend to like to choose this in such a way that my dA is going to point in the same direction as my B. Okay, so when I do that, that says that dA is going to be pointing in, which means I can find the direction that dl is going to go, and ultimately the direction I'm going to say the current is going to go, by using the right-hand rule. And so we can see that if I take my thumb of my right hand and I point it in the direction of dA, and then I curl my fingers, this says that my current is going to go around in this direction. That's also the direction I'm saying that dl is going to go. Okay, so now that we have that, what we can do is we can evaluate the right-hand side of Faraday's law. And that's to say that this is going to be negative partial derivative with respect to time of the integral. Now when I take this dot product, because I have this is going to go in and this is going to go in, this is just going to be B0 times 1 minus t squared divided by tau squared times dA. So because this is a circle, dA is going to be, it's a circular loop, and so dA is going to be 2 pi r dr. Okay. So now that we want to go about evaluating this integral, we're integrating over r. And the limits of integration are going to begin at 0 and go up to a. So this is r is equal to 0 to r is equal to a. Everything here is a constant except for this r, and so I can integrate over this r. And when I do that, I'm going to get an r squared divided by 2. Evaluated at a is going to give me a factor. Let me just write the whole thing. So this is the partial derivative of b0 times 1 minus t squared divided by tau squared. And when I do the integral, this 2 pi r dr is going to become just a pi a squared. Okay. So the next thing that I can do here is I can take the time derivative that I need here. And when I take that time derivative, I see that time derivative of 1 is 0. Time derivative of this term right here is going to give me a minus 2t. And I also have a negative sign here. So ultimately this says this is going to be equal to B0 with a 2 out front times t divided by tau squared times pi a squared. Okay, and this is going to be my right-hand side of Faraday's law. The left-hand side we evaluate exactly the same way that we evaluated when we did our circuit analysis. And so because of the direction that I chose for dA, I'm forced to have this loop go around in this clockwise direction. That's why I said that this dl points this way. So dl is going to go around this way. This is the same direction as the current, and so we remember our rules for circuit analysis. If the loop is going the same direction as the current, that means that this is going to give me a contribution of integral of E dot dl is equal to I times R. So this is I times R is equal to this. And now the last thing I need to do is I just need to divide both sides by the resistance to solve for I. And so what this says is I is equal to 2b0 T divided by R tau squared pi a squared. Okay? And that's it. So we went through the whole process of finding what the current is, and I labeled the direction of it here just by using Faraday's law. But what we can do is we can see if our answer is consistent with what Lenz's law will say. So we can look at that in two ways. The first way is to consider what is the direction of the force that is going to act on this loop if I know that the magnetic field is going to be pointing in, and I know that current is going to go around the clockwise direction. And so to determine that, what we can do is we can say that dF is equal to I dl cross B. And so what's the direction of dl? Well, we said that it's going to go around the circle in the clockwise direction. And so that's to say that my fingers have to point in that direction. It's going to go around like this. But let's just take a part right here and say that I'm going to try to find the force on this point. So when I do that, I point my fingers in the direction of dl, and then I have to curl my fingers into the direction of B. And so that means I actually have to, in this case, flip my hand over so that I can curl them into B, because B is going to be going in, I is going clockwise. So when I curl my fingers, my thumb is going to point in the direction of the force, and that says that here the force points like this. And everywhere we would find, if we did that process for every point on the circle, this says that the force is going to cause this loop to expand. Now we can see if that's consistent with what we expect it to be by considering what's happening to the magnetic flux. So if I plot this magnetic field as a function of time, so this is B of t, and this is t, it's going to do something like this. And so we see that for all times where t is greater than 0, this is going to be decreasing, right? It's getting more and more negative, and it's going down. And so what that says is I have less and less magnetic field going through this loop, and what the loop is going to try to do to keep the same amount of magnetic flux is it's going to try to expand. Okay? So that's Lenz's law, consistent with the direction that we had with Faraday's law. We can check that from another approach to think about what's the direction of the induced magnetic field. So we found from Faraday's law that our current is going to be, as a value is this, but it's going to be going around in the clockwise direction. Does that produce a magnetic field that counteracts the change of magnetic flux? And so if I put my thumb in the direction of the current, again, just at this point right here, and curl my fingers, that tells me that the induced magnetic field, so B induced, is going to be pointing in. Okay? And let's see if that induced magnetic field is consistent with what Lenz's law tells us. Again, we see that our magnetic flux is going to be decreasing because of the magnetic field that we're given here. And the induced magnetic field is going to be pointing in. So what this is doing is it's losing magnetic flux that's going through this loop. And the direction the current is going is it's trying to recover what it's losing. So the induced magnetic field is in the same direction as the original magnetic field. And again, that confirms the direction of the current that we found when we calculated this just with Faraday's law. Okay, so for all one of you that's watching, if there are any questions, I'll go ahead and answer them, and then I'll move on to the second one. This might be kind of a short session today. Okay, so let's go ahead and do the second question then. So, second question, same idea, slightly different setup. So in this case, rather than having some magnetic field that changes as a function of time, I'm changing what the radius of the loop is going to be as a function of time. And so with this question, what I give you is I give you some magnetic field that's pointing out. So magnetic field is just going to be some constant pointing out. and I have some loop of wire where the radius of this loop is going to change with time. And I say that this R of t is going to be equal to R0 t divided by tau. Okay. So what this says is that at time t is equal to 0, this has a radius of 0. And then as time goes on, the loop expands. We're not particularly concerned with why the loop expands. You could apply some force on this loop, have ropes tied to it, and some like imaginary horses pulling on it to make it bigger. We actually don't really care why it's getting bigger. We just say that it does get larger according to this function. And so what we want to do is we want to see, as a consequence of this loop getting bigger, what's going to happen to the current in the loop. How is there going to be a current that's induced by this loop getting larger? And so the first thing that we can do is write down Faraday's law. The integral of E dot dl is equal to negative partial derivative with respect to time, B dot dA. Okay. Again, first thing I like to do is define the direction of my dA. And so because my magnetic field is pointing out, I'm going to say that my dA is pointing out. So dA is pointing out, which means now that my dl is going to go around this way, right? Again, we can take the thumb of our right hand, point it in the direction of my dA. It curls around like this. And I also like to say that my I goes in the same direction as my dl. So that's my direction of the current, the direction of dA, and the direction of dl. So now that we have those things, we're ready to evaluate what the right-hand side of Faraday's law says. And so, again, the reason why I choose dA this way is so that this dot product is always going to be positive. And so we have a negative partial derivative with respect to time of the integral of B0 times dA. Okay? So in order to evaluate this, what we can do is we can plug in what dA is. So this is the integral B0 2 pi r dr. And then plug in our limits of integration here. So the lower bound for the limit of integration is going to be 0. The upper bound is going to be r as a function of time. So every time step that you have a different radius. And what we always want to do is we want to add up to what that radius is. And that radius is going to change with time. And so that's why our upper limit here is going to be r as a function of time. Okay. So this is a pretty straightforward integral. We've done plenty of these like this before, and so this says that this is the negative partial derivative with respect to time of B0. This is going to be pi times r of t squared. Okay. Now, in order to evaluate this partial derivative with respect to time, we can plug in what our r of t is, and so this is going to be minus partial derivative with respect to time of B0 pi times r0 squared t squared divided by tau squared. Okay. Let's go ahead and take our derivative here, and so this is going to give me a minus 2 b0 pi r0 squared t divided by tau squared. And again, what I told you in this problem was that this loop has some, I actually didn't explicitly say it, but I meant to. That this loop has some resistance of R. So loop has some resistance of R. And so what that means is this left-hand side, because I chose my current and my dl to go in the same direction, this is just going to be IR. And so IR is going to be equal to minus 2 b0 pi r0 squared t divided by tau squared. And to solve for what the resistance is, that's just to move, to solve for what the current is, we just move the resistance to the other side. Okay. And so this is what my current is. And what's kind of interesting about this is we see that the current actually varies as a function of time. So as time goes on, the current's actually getting larger and larger, or smaller and smaller because of the negative sign. So again, to revisit what this negative sign means, I made some choices and I said, I'm just going to pick dA pointing in the same direction as B0. and then run through the calculation and then see what comes as a consequence of the choice that I made here. And the consequence was that the current is actually not in the same direction that I drew it here. It's actually in the opposite direction. And that's what the negative sign is telling me. So now let's go ahead and check this answer to see if it's consistent with what Lenz's law is telling us. So let's redraw this here and put the current in the direction that it's actually going. So here's the direction the current's actually going. And my magnetic field is going to be pointing out. So let's figure out what the force is on this loop. So fingers in the direction of the current, curl in the direction of the magnetic field, tells me that the force is going to try to make this loop collapse. And this should seem to make sense because what's happening to this loop is by some outside mechanism, the radius is forced to expand. And that's enclosing a larger and larger region of magnetic field. And what Lenz's law tells us is that we don't want there to be a change in magnetic flux, or nature is going to act to oppose the change. Well, the change that's happening is the loop is getting bigger. So to oppose that change, the direction of the current is going to be such that it makes the loop try to get smaller. We can look at this the other way as well. And so we can think about what the direction of the current is going around here and what the direction of the induced magnetic field is going to be. So if the current goes in this direction, thumb in the direction of the current, curl in the direction of the magnetic field, that tells me that the induced magnetic field, B induced, is going to be pointing in. And so again, this is consistent with what we would expect to happen, because if this loop is expanding, it's enclosing more and more magnetic field that's pointing out. And to counteract that, the loop is producing a magnetic field that's pointing in. So it creates a magnetic field that points the opposite direction as the more and more magnetic field that it's enclosing. Okay? So actually, unless there are questions, I don't really have too much else to talk about. I'm going to I should do it tonight, to write some questions for homework for the coming week. And then I'll let you guys work on those, and then you're free to email me over the 4th of July. But I can't promise that. Let's say that I'll be in the proper state of mind to be able to answer your questions in an accurate and timely manner. I'm going to be in Texas visiting some of my friends from grad school. So visiting friends over 4th of July. You can imagine, again, I probably won't be in the right state of mind to be able to answer questions in a timely or accurate fashion, but I'll try my best. And it looks like we froze. Okay, so like I said, unless there are any other questions, that's actually just going to be it. Might as well unfreeze this. We got so far without this freezing, and then it always has to happen. It always has to happen. So I'll give you guys or you guys. I'll give the one person that's here a couple of seconds to type something if they have something that they want to ask. Okay, so that's going to be it. I'll see you guys, or again, the one person that's here in recitation tomorrow.